Good afternoon, students. A warm welcome to the afternoon lecture of refrigeration and air conditioning. So today we are in the lecture 15, and in the yesterday's class we have discussed about some of the topics and problems related to the compression cycle, standard compression cycle. Today in this class we'll continue those problems along with the actual vapor compression cycle and its problem, and also to the introduction to HVAC, right? So we'll start those topics today in this class. So in the last class we have stopped the problems. We have stopped at the problems concept. Now we are continuing the problem, and after 2 or 3 problems we are going to the other topic and problems to the topic, and also the other important topic which is discussed today, right? So who is the man coming? So he is the, one second, having some screen problem. Yes, see the next problem details. So here the vapor compression refrigeration machine, the refrigerant what we are using is refrigerant Freon 12, has a capacity of 12 tons. So it has a capacity of 12 tons of refrigeration operating between minus 28 degrees and 26 degrees. So what is the capacity of refrigeration? 12 ton refrigeration with refrigerant Freon 12, and the temperatures ranges from minus 28 degrees centigrade to 26 degrees centigrade, right? Now, and it is subcooled at 4 degrees centigrade. So at the subcooling process it is subcooled at 4 degrees centigrade before entering into the expansion device, and the vapor is super condensed by 5 degrees centigrade. So the subcooling temperature is 4 degrees centigrade and the superheated temperature is 5 degrees centigrade before leaving the evaporator. The machine has a 6-cylinder single acting compressor. So the compressor specification is, it is a 6-cylinder single action compressor with work with stroke equal to 1.25 times the bore. If it has a cleaner of 30% of stroke volume, so if we have the stroke and the diameter of the shaft, the depth of the shaft, and finally the remark for the 6-cylinder single acting compressor with stroke equal to the 1.25 times the bore. Stroke is equals to 1.25 times the bore. It has a clearance of 3% of the stroke volume. So what is the clearance it has given? The clearance is 3% of the stroke volume. Now determine what? Theoretical power required, COP, volumetric efficiency, bore and stroke cylinder. The speed of the compressor is 1000 rpm. The following properties of Freon may be used. The following properties of Freon may be used. Now here we'll see the table, right? See the first one, minus 28 degrees centigrade. For that minus 28 degrees centigrade, what is the bar you are having? 1.093 bar. The specific volume of the vapor is 0.1475, and the enthalpy in kg for liquid is 175 vapor, entropy 0.04, vapor 0.7. Coming to the other temperature, saturated temperature is 26 degrees centigrade, the pressure is 6.6, and the specific volume is 0.02, 60, 198.2, and zero point 0.6. So this is a total given question for the problem. Next, from the given question, write down the given data. So what is the given question? This is a lengthy question what they give. So based on that, write down the data. So what is it given here? Uh, mercury level is 12 TR. The mercury level is 12 TR. That is equals to T1 bar is equals to minus 28 degrees ante minus 28 plus 273 245. T2 bar అన్నప్పుడు T3 is equal to 26 అంటే 26 plus 23 299. T3 bar is equal minus T3 T3 bar minus T3 is equal to 4C or T3 is equals to 22, so 295. T1 minus T1 dash, that is equal to 5C or minus 223, so minus 23 plus 273 250K. None. What is L here? Length is equals to 1.25 the diameter of the object. Therefore, what is the clearance volume? The clearance volume is 3% of total volume. The clearance process is 3.4% for 5% of things. Now, what is the speed? Speed is equal to 1000 rpm. The speed is equal to 1000 rpm, and v1 dash is equal to 0.1475 meter cube per kg. V2 dash is equals to 0.0262, and hf1 is equal to 10.64. hf3 dash is equal to 60.67. hf1 is equal to 175. hh2 is equal to 198.11. So like this, the given data, entire given data is given. So what is SF3, SF2, SF? Read the question. Now S dash, S1 dash, S2 dash. Therefore, was the question is completed. What is the CPV? Right. So once in a CPV, other people do. So once in a so okay. So we are having the given values. So based upon the given values, write down the TS and PV diagram shown in the figure. So once you draw the PV and TS diagram, entropy and enthalpy, it will be easier to draw the entropy figures, right? Now, so based upon the graph, what it is saying. Now, now see here. So there is a temperature line. This is a entropy line. So entropy line is on the x-axis, temperature line is on the y-axis. So here we are having 1 dash, right? 1 dash, 2 dash, 3 dash, 4 dash. So once you got 1 1 dash 2 2 dash, see here. So the theoretical power required. So what is happening in the initial thing? The given data, what is the question given? Theoretical power required. So in this theoretical power required, the find out the temperature of the superheated pressure at junction 2. So therefore at entropy at point 1, S1 is equals to S1 dash plus 2.3 CPV log T1 by T1 dash. So substituting S1 value, substituting 2.3 CPV log T1 by T1 dash. T1 dash. So substituting the values here. So directly you are getting the value 0.7277. Therefore at entropy point 2, at entropy here, that entropy is at point 1. Here the entropy is at point 2. So here the S2 value is equal to S2 dash plus 2.3 CPV log T2 by T2 dash. So substituting the values S2 dash 2.3 log T2 by 299. Therefore S2 value we got it. Now what is the thing? So point 1 and point 2. Since the entropy at point 1 is equal to point 2, point 2 following the equations. Therefore, 0.7277 is equals to 0.666 plus 1.145 log T2 by 299. T2 by T2 by 299. T2 by 299. Now we know the enthalpy. So already we know the enthalpy point at 1. We know the enthalpy point at 1. We know that the enthalpy point at 1 is, we know that the enthalpy point at 1, H1 is equals to the enthalpy point at H1 dash is H1 dash plus CPV T1 minus T1 dash. So keep the value of H1 dash, CPV in the before slide, this one, and temperature T1 minus T1 dash, that is 178.15. Now the enthalpy at point 2, H2 formula, H2 is equals to H2 dash plus CPVC T2 minus T2 dash, that is equals to 210.8. Now the enthalpy at the liquid refrigerant, the enthalpy of liquid refrigerant at point 3, HF3 is equal to HF3 dash minus CPT T3 dash minus T3. So this is the value what we have got. Now the heat extracted affect the refrigerant effect per kg of the refrigerant. Therefore heat extracted RE is equals to H1 minus HF3, that is equal to 178 minus 64, that is equal to 113.66. And the refrigeration capacity of the system Q is equals to 12 TR, that is equal to 12 into 210. Now the mass flow of the refrigerant, therefore the mass flow of the refrigerant MR is equals to Q by RE. What is the Q here? 2520. RE is equals to 113.66. That is equal to 22.17 kg per minute. Now The work done during the compression of the refrigerant. The work done during the compression of the refrigerant is equals to, this is the formula. MR H2 minus H1, that is equal to 22.17. MR what we got, and H2 value we know that, H1 value. So this is the value what we got. Then the theoretical power required is equals to 724 by 60, that is equal to 12.07 meter, 12.07 kilowatts. The same way, find out the coefficient of performance of the machine. The coefficient of performance is equals to H1 minus H3 HF3 divided by H2 minus H1. So this is the value H1, HF3, H2 minus H1, this is a 3.48. Next, volumetric efficiency. So the third point to be find out is volumetric efficiency. So in this volumetric efficiency, V2 is a specific volume at the point 2. Then C is equal to clearance, that is given 3% in the question, that is 0.03. Therefore, applying the Charles law at point 1, V1 by T1 is equals to V1 dash by T1 dash. T1 dash. That is equals to V1 is equals to V1 dash into T1 by T1 dash. That is equals to V1 into T1 by T1 dash. That is equals to this one. Now the Charles law applying at the point 2, V2 by T2 is equals to V2 dash by T2 dash. That is V2 is equals to V2 dash into T2 by T2 dash. That is equals to this value. Therefore, the volumetric efficiency is equals to 1 plus clearance minus clearance into V1 by V2. Therefore, 1 plus 0.03 minus 0.03 V1 by V2, that is equals to 87%. We are having the volumetric efficiency. Now, what is the bore and stroke of the cylinder? Let D is equals to bore of the cylinder. This should be very close. This should be very close, right? And L is equal to length of the cylinder, that is equal to 1.25 D, and N is equal to speed of the compressor, that is 1000 RPM. So directly we got the values. Now find the theoretical suction volume or a piston displacement per unit is equal to MR into V1 into 1 by the efficiency. We got the value MR 22.17 into V1 value 1 by efficiency, that is 3.84 meter cube per minute. Now the machine has 6 cylinders as shown in the figure. It has 6 grass-hopping machines like. So we are having the 6-cylinder single acting compressor. Therefore the piston displacement per cylinder per minute is equals to 3.84 divided by 6. 3.84 divided by 6. Now the suction volume or a piston displacement per unit is equals to piston area into stroke into RPM. So what is the piston area? Pi d4. Pi d pi by 4d square into stroke is equal to L. RPM is equal to N. Therefore pi by 4 into d square into 1.25 d into 1000. That is equal to 982 d cube meter cube per minute. Therefore, applying the equations 1, 3 and 4, this 3 and 4, d cube is equals to 0.64 divided by 982. That is, after simplifying it, we got the value d is equals to 86 mm. Therefore, L is equals to 1.28466 mm. That is equals to this and this. Right? So this is the length and this is the diameter of the tube. Hope you understood. Now we'll see the next topic, actual vapor compression cycle. So in the actual vapor compression cycle, what happens? Here, the cycle differs from the mechanical theoretical vapor compression cycle. So the actual compression cycle differs from theoretical vapor compression, where unavoidable and causes losses. The main deviations between the theoretical cylinder and the actual cycle are, see here, we are having then temperature on the y-axis and entropy on x-axis. Here the 1 to 2 is a straight, and 2 to 3 is somewhat straight, and 3 to 4 is going down and again rising up. So another point, PC and PP, 8th point and 9th point, did no information, right? See here, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, 6 to 7, 7 to 8, 8 to 9, and 9 to 10. So what are the deviations here? The vapor refrigerant leaving the evaporator is in superheated state. So in the actual vapor cycle ki, theoretical vapor cycle ki difference ఏంటంటే, the vapor refrigerant which is coming out of outside of the evaporator is superheat in the state. Next, the compression of refrigerant is neither eccentric nor pantographic. So what is the second point saying? The compression of right. So here the compression of the refrigerant the compression of the refrigerant is neither this isentropic nor polytropic. The liquid refrigerant before entering the expansion valve is subcooled in the condenser. So what happens in the third phase? That liquid refrigerant before going to the expansion valve, it is compressed in the condenser. The pressure drops in the evaporator and condenser. So these are the main points to discuss regarding the actual vapor cycle, right? Actual vapor cycle. The pressure drops in the evaporator and the condenser. So based upon this actual vapor cycle graph, or based upon the question, we will discuss some of the problems. Right. So coming to the some of the problems, a simple ammonia compression system operates with a capacity of 150 tons annamata. The condensation temperature in the condenser is 35 degrees. The evaporation temperature to the brine cooler is minus 25 degrees centigrade. The ammonia leaves the evaporator and enters the compressor at minus 8 degrees centigrade. Ammonia enters the expansion valve at 30 degrees centigrade. The wired air drawing through the compressor valves suction is equal to 0.118. Diagonal bar is equals to 0.248. Right? 2 3 bar. Compression index is equal to 1.22 and volumetric efficiency is equals to 75 percentage. Right? 75 percentage. Now, first write down the calculation what we require. So determine the power, heat transfer to the cylinder, and piston displacement, heat transfer in the condenser, and coefficient of performance. So generally make use of all the given data available in the question and start framing the problems. So what is the given data in the question? The energy is given as 150 tons and T2 is equals to T3 dash. T2 dash is equals to T3 dash is equals to 35 plus 30k plus 273 plus 308k. Now T2 is equals to T2 dash, that is equal to T3 is equal to 35, and T1 double dash is equal to T4, that is equal to minus 25. T1 is equals to minus 8 degrees centigrade, so on so, and N is equal to 1.22 and efficiency is equals to 0.75. So now draw the TS diagram and PV diagram and start doing the pH diagram by finding the pressure regarding the evaporator. So here in the pH diagram we find that the pressure corresponding to the evaporator temperature is minus 25 degrees centigrade. Therefore P1 is equals to P1 double dash, that is equal to P4, that is equal to 1.518 bar. Since there is a suction pressure drop, therefore at point 1 P1 dash is equals to 1.518 minus 0.118, that is equal to 1.4 into 10 to the power of 9. Now the pressure corresponding to the condensation temperature at 35 degrees centigrade is equals to 13.5 bar. Therefore so what's happening here? Therefore, the discharge pressure drop of 0.2523 bar is twice that of the drawing. Due to the wide drawing, the pressure at the point 2 is equals to P2 dash is equals to 135 plus 0.23. That is equal to 13.73. Now see the PV diagram and TS diagram. So here the pressure enthalpy and the pressure enthalpy is here 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So we are having a double enthalpy, double problems. So the T1 diagram, T1 value, T1 dash, T2, T double to T2, T2, T2 double dash, T2 dash. The same way if we see the temperature and entropy, the temperature at T1, one double dash and 1 dash and 3 dash. Now based upon this problems, now see here the H1 value is equals to 1440. The specific volume at the point 1 is equals to V1 dash is equals to 0.8 meter cube per kg. Now the temperature at 1, the temperature at T1 dash is equal to 64 and V2 is the specific volume at 2. The compression is according to the PV square to PV to the power of 0.2 VC and see here the P1 V1 is equals to P2 V2, right? Now V2 ని ఈ పక్కకి తీసుకొస్తే సో ఈ వాల్యూస్ అన్ని ఆ పక్కకి మీరు రైట్ సైడ్ వేసుకుంటే we have the values V1 square, P1 1.4, P2 13.73 and 1 by N. So directly we are getting the value 0.123 meter cube per kg. Now plot the point P2. So therefore finding for PV diagram how to plot. So last time. So here we have plotted in this manner. Now enthalpy of supersaturated ammonia, enthalpy of supersaturated ammonia at point 2 is equals to H2 is equal to 1620. Therefore the temperature T2 is equals to 90 degrees and the enthalpy at T3 H4 is equal to 320 kilojoules. Now power P, the power P, we know the refrigerant and effect per kg RE is equals to H1 minus H1 minus H1 minus HF3, that is equal to 1440 minus 320, right? And the refrigeration capacity, mass flow of a refrigerant MR is equals to this one. Now the work done by the compressor per minute MR work done is equals to MR into N of N minus 1 P2 V2 minus P1 V1, that is equals to, apply the value directly and get the value. Therefore the power P is equals to 800 divided by 60, that is equal to 14.18 bars. Understood? So we'll stop the class here as I have some technical problem, so it is not going to the next slide. So we'll stop the class here. We'll continue in the next class.